Hi, today's lesson is going to be about functions. There are three main things we need to learn. One, what is a function? Two, how to evaluate a function. And three, how to graph a function. Now we're just going to talk about those three things, not in huge detail, but the basics and a couple of small other things that go along with it. So we start with the idea of talking about a relation. Now, a relation is any set of ordered pairs. So those ordered pairs could be numbers, letters, colors, it doesn't matter. If you have a set of ordered pairs, that would be considered a relation. There's not much to it. The idea being, if you look at, say, like this set of ordered pairs here, this would be considered a relation because it's just three ordered pairs put together. That's considered to be a set of ordered pairs. So the idea when you look at these ordered pairs is they have two components to them. They're pairs. So there's a first component and a second component. So the idea is the first component for each of them is considered to be your domain for your ordered pair. And the second component to each of them is considered to be your range. So 1, 2, 3. These three would be my range for this relation. So, I mean, that's it. There's not much to it, like I said. That's a relation. Now, we don't deal with relations very much. I mean, the only reason we really need to talk about relations is so we can get to the next thing, which is this idea of functions. So, a function. Now we'll label it f, and you look at this f right here. That we'll talk about in a second. That's sort of, we're going to name a function, and we don't have to use f, we can use anything, but we'll talk about that in a second. So first, definition. A function from set A to set B is a relation that assigns each element x in the set A to exactly one element y in set B. The set A is considered to be the domain, and the set B is considered to be the range. Now, you read that, it might not make a whole lot of sense, but the idea is a function is, one thing you need to get out of it is it's a type of a relation. You see here, it's a type of a relation, so that means it's a set of ordered pairs, and it groups the ordered pairs in a specific way, such that each element in the domain gets matched to exactly one element in the range. And this is a key word, exactly one element in the range, or the second set. So the easiest way to think about it, I think, is to look at it like this. Set A, set B. Here's set A, here's set B. Okay? So you're starting with set A has to get matched up with set B. Like this. But it gets matched up in a specific way so that each element in set A gets matched to exactly one element in set B. Now if that happens, this particular relation is then a function. So look at this relation right here. It has domain values 1, -5, and 7. Okay, now 1 gets matched up with 3, -5 gets matched up with 4, and 7 gets matched up with 3. So the question is it a relation? We already said yes. It's a set of ordered pairs, so it's a relation. But looking at it in this sort of mapping method is a better way of sort of looking to see if it's a function. Now, does each one of these values in set A get matched to exactly one value in set B? And the answer is yes. Now, a lot of people might say no because of the 3. 1 goes to 3 and 7 goes to 3. But does this one go to 1? Yes. Does this go to 1? Yes. Does this go to 1? Yes. So does each element in set A get matched to exactly one element in set B? Yes, this is a function. I think when you see the ordered pairs, it's easier to draw this mapping picture and then see if you have a function by, does it follow the definition? Does each element in set A get matched to exactly one element in set B? And that's the key, exactly one element. The next part is, okay, well, what's the domain and what's the range? Well, the domain is everything in the first set, and the range is everything in the second set, or essentially the first component of every ordered pair is my domain, and the second component of every ordered pair is my range. So this would be considered my domain, and this would be considered my range. Now I have to give you a couple more examples. So, because there's a couple of main things that happen here. When you look at this, you know, you have your basic definition. Each element in set A must be matched to one element in set B. And the idea is exactly one element in set B. That's your definition. Now, a couple of things you got to worry about. Some elements in set B may not be matched with any element in set A. That's fine. Two or more elements in set A may be matched with the same element in set B. We just saw that in the last example. And then the fourth thing is an element in set A, remember that's our domain, cannot be matched with two different elements in B. So we're really making sure that as long as it follows the definition of each element in set A must be matched with exactly one element in set B. So here's my sets, okay? Set A, this is my domain. Set B, this is my range. So I look and I go, okay, here's a couple of elements. I'm not even going to give them names. I'm just going to put dots. And the idea is here's a couple of elements here. So the question is, this gets matched here. This gets matched here. This gets matched here. Is this a function? Is my domain here, supposed to be a D, is my domain getting matched to my range in the way that each element in the domain gets matched to one element in the range? So clearly this one, yes, this is a function. Okay, here's another one. Set A, set B, domain, range, whatever you want to call them. Here's set A, here's set B. So I have a couple of elements here, 3 elements there, 3 elements, or let's say 2 elements here. This one gets matched to this one. This one gets matched to this one. This one gets matched to this one. So is this a function? Does each element in A get matched to exactly one element in B? Well, the answer here is yes again, because this one goes to 1, this one goes to 1, this one goes to 1. They're all going to the same one, but that's fine, as long as each element in set A gets matched to exactly one element in set B. Alright, so let's look at something where it doesn't work out. Okay, so if I give you here's set A, here's set B. Alright, A elements, B elements, this one gets matched here, this one gets matched here, and this one gets matched here. But then let's go back to the first one and say that one also gets matched here. So this is not a function. Not a function at all, because here this element gets matched to 2 elements here. So 1 element in A gets matched to 2 in B, not a function. Alright, so you can see that. So how about we do another one? One more. Set A, set B. Again, this is, remember we call this the domain. This is my range. So here's some A elements, here's some B elements. So this gets matched here, this gets matched here, and this one doesn't go anywhere. Is it a function? The answer would be no, because each element, key is each element in set A has to get matched to exactly one element in set B. This one goes to 1, this one goes to 1, this one doesn't go anywhere. Now, we can fix this by saying, all right, let's take this element and just delete it. Okay? Don't put it in our domain. Well, if we don't put it in our domain, then it would be a function because this goes to 1, this goes 1, and this one's not here. So it technically would be a function then, but you know, how are we going to just take it out? Well, we just shouldn't put it there in the first place. So here's a couple of crazy things that do happen with functions, and you got to determine if you do or don't have a function. So there's one more thing we need to talk about, and that's the idea of the names of these two sets. So we said set A, set B, we said domain, we said range, and that's right. Domain and range probably the most common, but we can also just label them by sort of variables, typically X and Y, and that has to do with, you know, when you look at an ordered pair, the first component is your X and the second component is your Y. So, you know, if we're looking at, say, like an equation, the X component would be from the first set, the Y would come from the second set. But we could also label them as independent variables and our dependent variables. So this would be our dependent variable would be our second set, and our independent variable would be our first set. So, you know, 4 different really ways to do it. Set A, set B, that just sort of came from the definition. Domain and range, that kind of, it comes from the idea of, you know, sort of thinking of more along the lines of these sort of sets. X and Y are variables, more or less equations, formats of functions, and then that sort of goes along with those independent and dependent variables. Okay, so now you're not always going to see a function represented by the 2 circles set notation that we were just looking at. Most of the time you're going to see functions written as equations. So we have, you know, this equation here, 2x squared plus y plus 1 equals 0, or this other equation, y squared equals x. So to determine whether or not these equations are functions, you have to make sure that it follows the definition, which is that each x gets matched to exactly one y. Now you don't have that picture that we were looking at before where you draw your 2 ovals and see if one x gets matched to one y, but you can do much the same thing. Take this equation, this first equation here, solve this equation for y. In that case you get y equals negative 2x squared minus 1. So that equation solved for y. Now when you solve it for y, you can then look and see if I plug a particular x value in here, will I always get 1y from that? Well, think about it. If I plug something in for x, okay? If I plug something in for x, some number, if I plug that in for x, what am I going to do to it? I'm going to square it. So let's say I plug in, I don't know, 3. So I'll take 3. I'll square it. Then what am I going to do? I'm going to multiply it by negative 2. And what's happening there? Well, if I square 3, I get 9, a single number. And if I take any number and plug it in for x and I square it, I will get a single number as an answer. Then I multiply that by negative 2. Well, 9 times negative 2 is negative 18. But that should work, same idea with any number. I plug any number in for x, I square it, I get a single number. I multiply that by negative 2, I get a single number still for this whole piece. Then the last thing I'm going to have to do is subtract 1 from it. So in this case, y is going to equal negative 18 minus 1, negative 19. Okay? That's a single number. So for 1x I plugged in, I just made up 1, 3. I got 1y, which is negative 19. Now, if I did that for any other number, I'm going to plug a single value in for x, and using these operations, I'm going to get a single value for y. Therefore, 1x gives me exactly 1y. This is a function. So this equation represents y as a function of x. Now let's look at b. if we look at b, the common question is, well, shouldn't that happen all the time? Shouldn't every equation be a function? The answer is no. If you look at b, if I have to solve for y first, and that's the key, solve for y. If I have to solve for y first, well, I gotta get y by itself. So I gotta get rid of the square. So how do I get rid of the square? I have to take the square root. So if I look at this, I'm gonna go, okay, well, that means y equals the square root of x. There's something you learned in algebra, and something you learned in algebra was if I take the square root of both sides of the equation, which is what I did here, I have to have a positive and the negative square root. The reason behind that is squares. If you square a positive or you square a negative, the answer is always non-negative. So it does away with negatives. So if I'm going to get rid of that square, I have to reintroduce those negatives to the problem. So that's where this plus and minus come from. But now look at this. If I plug a single value in here for x, let's say, I don't know, x equals 4. What's going to happen? Y is going to equal plus or minus the square root of 4, or plus and minus 2. So then what do I have? I have 1x of 4 getting matched to 2y's, positive 2 and negative 2. So 1x, 2y's, not a function. Now, the key to this right now is this right here, okay? Plus and minus. If that plus and minus pops up while you're solving for y to determine if y is a function of x, then it's not going to be a function, because that's going to be 1x, 2y's, doesn't follow the definition. If that doesn't happen for these algebraic equations, then it's going to be a function. So remember when you need that plus and minus. Anytime you have to take the even root of both sides of an equation, that plus and minus is going to pop up, not a function. But the key to representing an equation as a function is to solve for y. So we don't want to have to do this all the time. We want to look at an equation and automatically know it's a function. So the way we can do that is by what we call function notation. So if I look at this first equation, a, and I solve for y, so I don't have to check to see if this is always in a function. What I can do is I can replace the y with what we call function notation, which is this f of x notation. So that means f of x, this is what we're going to replace y with. We get f of x equals negative 2x squared minus 1. Instead of y equals negative 2x squared minus 1. And the purpose of this is a couple of things. One, now when we look at this equation, we don't have to think, is it a function, is it not a function? It's a function. It's in function notation, f of x notation. Now this f of x that we're looking at here, there's a couple of parts to this. One is the f, okay? That f is the name of the function. That letter right there that we use is the name of the function. It doesn't have to be f. Some common ones. F of x, g of x, h of x. These are common ones. This is just f, g, h are the names of these functions. Actually, you don't have to use those letters. That's just the common ones. I could say smiley face of x. It doesn't matter. Whatever I put in front of this x, that's the name for this function. And obviously we would not really do this, but that's the key. That letter out in front, all it is the name of the function. More importantly is the letter inside the parentheses. That variable right there is what we consider to be the independent variable for the function. Remember, we talked about this idea, domain, independent variable. They basically mean the same thing. This variable is telling me what the variable of the function is. That is very important, because if you look, this variable is the same variable that's over here. It's the variable of the function. It's the independent variable. So when you're looking at function notation, the first letter, F or G or H, whichever ones you use, again, these are the common ones, is the name of the function. So if we have a bunch of functions we're working with, we know which one we're working with at each time. Function F, function G, function H. The variable inside the parentheses, remember this is read F of X, the variable inside the parentheses is the independent variable, okay? It's the domain variable. It's the starting variable. And that should be the same here. We can change that variable, but we got to make sure that it all matches up. The next thing we have to do is learn to evaluate a function. So here's a particular function, f of x, and f of x equals negative x squared plus 4x plus 1. Now, I don't have to check to see is this a function. Given that it's written in function notation, I know it's a function. So the next thing I want to do is evaluate that function. I want to plug something into this function and figure out what the answer is. So let's do A, f of 2. So we want to find f of 2. What this is telling me is that when x equals 2, what does 2 get matched up to? What's the y value for this particular x value? So this function tells me, okay, if I'm finding f of x, this is what I should do. I should take it, square it, multiply it by a negative, add 4 times that x, and then add a 1. So what I'm really going to do is just essentially take this 2 and plug it in every time I see an x, because x is 2. So if I want to find f of 2, I'm going to do negative 2 squared plus 4 times 2 plus 1. And all I really did was take the 2 and plug it in every time I saw an x. Now, one thing you gotta remember here is just some algebra. This negative is outside the square. You do the square first and then a negative. That's very different than if the negative was inside the square. So what I end up with is 2 squared is 4 times a negative. I get negative 4 plus 8 plus 1. So I end up with negative 4 and 8 is negative, or is positive 4. 4 and 1 is 5. So f of 2 equals 5. And what that's basically telling me is that 2 is getting matched up with 5 through this function. This is my independent, this is my dependent value. This one right here is my domain, this right here is my range. So we can do this for all sorts of values. If we want to do the next one, find f of 3t. Well, I'm going to plug 3t into this function instead of 2. Well, I'm going to do the same thing. It's the same function. So I'm going to take negative 3t squared plus 4 times 3t plus 1, and that's going to be f of 3t. Now, I should simplify this a little bit and evaluate it, but generally, if you look, the same thing I did with the 2 here is the same thing I'm doing with the 3t here. I'm plugging it into this function when I see an x. Okay? So what I get is 3t squared. That's 3t times 3t, which is 9t squared. Multiplied by a negative is negative 9t squared. 4 times 3t is 12t plus 1, and that's the best I can do. I can't simplify this anymore, so that's what f of 3t equals. Sometimes you'll get just a number, sometimes you get another function. It depends on what you're plugging in and what the function is you're working with. But basically here, 3t is getting matched up with negative 9t squared plus 12t plus 1. Okay. Alright, do another one. How about f of x minus 2? Okay. Now, f of x minus 2. What a lot of people think is, well, it's just f of x and we subtract 2 from it, but that's not the case. I'm not going to take this original function that I'm looking at and just subtract 2 from it. What I have to do is plug x minus 2 in. This thing is like the 3t is like the 2. I'm going to plug x minus 2 into the function like I plug 3t into the function, like I plug 2 into the function. So I'm going to have negative x minus 2 squared plus 4 times x minus 2 plus 1. And if you look, it looks a lot like everything else we've been doing. So now what do I have to do? Well, that's essentially the answer, but I should simplify it. I should multiply this out, collect like terms. So if I do that, what I have is negative x minus 2 squared. That is not x squared and then 2 squared. When you do x minus 2, you got to do x minus 2 times x minus 2. Remember, algebra would be x minus 2 times x minus 2. You FOIL this out and you end up with x squared minus 4x plus 4. Okay. So that's that. I distribute this 4 in here and here, and I get 4x minus 8 plus 1. Distribute this negative in here through this, and I end up with negative x squared. This will get me negative, and a negative gives me positive 4x, and another positive 4x gives me 8x. Here this will be negative 4, negative 8, positive 1, negative 4, negative 8 is negative 12, plus 1 is negative 11. So f of x minus 2 is negative x squared plus 8x minus 11. Okay, one more. This is an important one, but this one's a lot like the previous one. Find f of x plus h. So let me get rid of this. Give me a second. Okay, so look at I'm leaving the first one up there for a reason. If you look at that first one, and all the other ones we've done has sort of followed off of that. If you look at that first one, we found f of 2 when we plugged 2 in for x. Well, if I want to find f of x plus h, I should do the same thing. Again, a common mistake with f of x plus h is a lot of people think you just add h onto the end of this function here. But that's not the case. What I'm going to do is plug x plus h into the function. Okay? So, if I wanted to find f of x plus h, I should do it like I did with 2. I should have negative x plus h squared plus 4 times x plus h plus 1. That's how I'm going to find f of x plus h. Now if I'm going to square x plus h, I can't just square the x and square the h. This is x plus h times x plus h. So if we do a little bit of side work here, I'll do x plus h times x plus h. Okay? That would be x plus h squared. So if I distribute this out, I get x squared. I'm going to get an x times an h, another x times an h, and I'm going to get an h squared. So I have x squared plus 2xh plus h squared. Now there are faster ways to do this. You should have learned in algebra. There's a formula for these squares. Essentially this right here is the formula. But really all you need to be able to do is come up with the answer. So whether you remember the formula or you got to do it this long way and write it out, that's how you square x plus h. Do not say x plus h squared equals x squared plus h squared. That is not true. You cannot do that. Okay? Because this is how you do it. Alright, back to the problem. So this becomes negative x squared plus 2xh plus h squared plus, distribute this 4 in here, 4x plus 4h plus 1. Collect any like terms if possible. There really aren't any. All you really have to do is distribute this negative through and you're done. So we get negative x squared minus 2xh minus h squared plus 4x plus 4h plus 1. So this would be f of x plus h. And you can clearly see it's not just, oh, let's look at the original function, put an h on the end. That's not what this is saying. This is saying take x plus h and plug x plus h into the function every time I see an x. Okay? And that's what we did. Okay, here's another tricky one. This function right here is what we call a piecewise function. We'll talk about more about this piecewise function in the next section, but this piecewise function has two functions associated with it essentially. Now these functions have specific domains in that if you look at this one, x squared plus 1 is one of the functions. That only works if x is less than 0. So if the domain is less than 0, that's when you will use this piece. This other piece here, x minus 1, has a domain of x greater than or equal to 0. So only if x is greater than or equal to 0 will you use this piece. The key to a piecewise function is the domain. If you know what your domain is, if you know where to put something, then you can evaluate this piecewise function. So x is less than 0, we use x squared plus 1. X is greater than or equal to 0, we use x minus 1. So let's evaluate the function at these three values. So let's find f of negative 1. Well, if we want to find f of negative 1, I got to know what piece to evaluate this function with. Well, negative 1 is less than 0. So if negative 1 is less than 0, I should be using this piece. So I say, alright, well, if I'm going to use that piece, what do I have to do? I have to take negative 1, square it, and then add 1. Because that's what the function is. This function is x squared plus 1. So if I did that, what would I get? I would get negative 1 squared is 1 plus 1 is 2. So f of negative 1 is 2. Okay, let's do another one. F of 0. Well, 0 is equal to 0. In that case, I have to use this function. Because this function says when x is greater than or equal to 0, this is the piece we use. So x is, in this case, equal to 0. So I'll use that piece, which is just says take my x and subtract 1. Equals negative 1. So f of 0 equals negative 1. Let's do one more. So if we do f of 1. F of 1, well, 1 is greater than 0. So I'm going to use the same exact function again, because this function is for x greater than or equal to 0. So that should be 1 minus 1 equals 0. Now the key is, I have to know where to put my value. I need to look at these domains. These two things cannot overlap. X is less than 0, x is greater than or equal to 0. They don't overlap. If, for some reason, I had, say, this. X is less than or equal to 0, x is greater than or equal to 0. These two things overlap, which means if I had an x value of 0, like this one, I wouldn't know where to put it. I could put it in this function, I could put it in this function, because they're both for equal to 0. And therefore 1x would get me 2y's and not a function. So the key is, your domain can't overlap in the piecewise functions. So we'll deal more with piecewise functions in the next section, but for right now, that's the basics. Now we need to talk a little bit more about domain. So we already said that domain is essentially the starting variable, x in most cases. But we need to talk more about domain in terms of, some domains are explicit, some are implicit. The idea of some domains contain all real numbers, some domains don't. So the idea of domain is all the values that you can plug into a function. So when I showed you this picture before, this is my starting set, this is my ending set, and we do something like this. This was the domain, and this was my range. Okay? So remember, the definition of a function. Each x gets matched to exactly one y. So each value in my domain gets matched to exactly one value in my range. Well, if that's the case, I gotta make sure that my domain contains values that go somewhere, that give me an answer. And if a value doesn't give me an answer when I plug it into a function, I don't want it in my domain. So the domain is the set of all values that go somewhere, essentially. So different types of functions have different domains. Polynomial functions. This right here is a polynomial function. The domain for this function is all real numbers, or the interval negative infinity to positive infinity. Why? Because no matter what value I take, I plug it in for x here and here, I'll always get an answer. Positive numbers, negative numbers, zero, fractions, roots, it doesn't matter. If I plug an x value in, some value in, I'll always get an answer. But that's not always the case. So the domain for this is all real numbers. Now there's different ways I can write that. I could say the domain is all real numbers. A symbol for all real numbers is this. That's the symbol that states all real numbers. I could write it in interval notation. I could say that the domain is negative infinity to positive infinity. I could use set builder notation. Set builder notation is to use these braces, and I would say the brace, the domain is all x such that x is a real number. And that's what we call set builder notation. The way you read this is all x such that x is real. Now, I really don't care how you do it. Probably interval notation is your best bet. Writing it out in words is pretty helpful too. This class being online and everything being multiple choice, you really need to get familiar with interval notation. Alright, but not every function has the domain of all real numbers, where I can just plug whatever I want in. Some functions have restricted domains, and that's going to be a major part of a lot of what we do this semester, is this restricted domain problem. So, two major issues when it comes to algebraic functions: fractions and radicals. So let's look at fractions first. One thing you understand with fractions is that fractions are really division. And when it comes to division, you cannot divide by 0. So that means the denominator of the fraction cannot be 0. Let's look at this fraction right here. The denominator, x squared minus 1. If x equals 1 or negative 1, x squared minus 1 equals 0. So the idea is, if I tried to find f of 1 or f of negative 1, I would get an undefined answer, which means I don't have an answer because I get 0 in the denominator. I would get 1 over 0. You cannot do 1 over 0. This cannot happen. So since 0 can't be in the denominator, and when I plug 1 in, I do get 0 in the denominator here, 1 cannot be in my domain. So if I want to write that somehow, I could say the domain is all x except x equals 1 and x equals -1. Right? That's one way to do it. And that's just sort of writing it out in words. But you probably want to do interval notation. So interval notation would be the domain is -infinity to -1 union -1 to 1 union 1 to infinity. Now look at what I did here. I used a parenthesis here, 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 here for a reason. Now, interval notation, you gotta remember that parentheses means I don't include this value, and a bracket, if I did brackets, that meant I do include the particular value. So I don't want to include -1 or 1. Now, I put parentheses around the infinities because you can never include infinity in anything. Infinity is like a moving target. Once you think you got to infinity, just keep going because you didn't get there. You can never get to infinity, and therefore if you can never get to infinity because it's constantly moving, it can never be included. So we have parentheses around the infinities, but we also have to put parentheses around the 1. So this means I want to include all my x's from -infinity up to -1, and the second I get to -1, I don't want to include that value. Then I want to union that with -1 to 1, and I want everything between -1 and 1, but I don't want to include those two values again. And then I want to go from -1 all the way up to infinity, but again, -1's not included. So this is saying the same thing that the original one is saying, that all x except x equals 1 and x equals -1. They're saying the same thing, but the second one is interval notation. So that's my domain. So when it comes to fractions, you look at this fraction. This is called a rational function. You do not want the denominator to be 0. And if there's a particular value that would make the denominator 0, essentially if you look at this equation here, if I solve this equation, those are the things that I don't want in my domain. So you look at this more in terms of what you don't want than you do want, but the domain should be all the things that you do want to plug into the function. And sometimes it's easier to look at what you don't want, especially when it comes to the fractions. All right, one more, radicals. Radicals are roots. Now, when it comes to odd roots, there's not very many issues because odd roots are usually fine with most values. You can take the odd root of a negative, you can take the odd root of 0, you can take the odd root of a positive. That really doesn't matter. You can take the odd roots of a lot of numbers. It's even roots that are the issue. So when you look at this, if the index is even, then the radicand cannot be negative. Radicand meaning the thing inside the root. You cannot take the even root of a negative number. If you try and take the even root of a negative number, you will get an imaginary answer. And we're dealing with real numbers right now, so imaginaries don't work for us. So when I look at this function here, f of x equals x minus 2, this thing inside the root, x minus 2, cannot be negative. What does that mean? It has to be greater than or equal to 0. And when x minus 2 is greater than or equal to 0, those will be the values that satisfied my domain. Well, if you look at this, this is very easy to solve this inequality. I'll add 2 and I get x is greater than or equal to 2. These are all the values that are in my domain. These are all the values that x minus 2 won't be negative. It'll be greater than or equal to 0. So x is greater than or equal to 2. So I could say the domain is all x greater than or equal to 2, or I could write in an interval notation and say the domain is all the values greater than or equal to 2. In the interval notation, that means 2 to infinity. Now, or equal to 2, I want to include 2, so bracket, but always parentheses around the infinity. And this is greater than or equal to 2. This will be the interval notation for my domain. So to sum it all up, polynomials, the domain will always be all real numbers. Rational functions, okay? These are the fractions. The denominator cannot be 0. Any value that makes that denominator a 0 will not be in the domain. Radicals, even roots, this is a square root. Even roots, you cannot have a negative inside that even root. So the domain is all the values that don't make it negative, all the values that make it greater than or equal to 0. If this were an odd root, the domain would be all real numbers, because you can take the odd root of negatives, you can take the odd root of 0, you can take the odd root of positives. So there's no issues with odd roots. The issue is with the even roots, and you cannot take the even root of a negative number. Another major thing we need to talk about is graphs of functions. Now we'll talk more about graphing specific functions later. But what we need to do is just generally talk about the graph of a function and how it's related to graphs we've seen before. You should be familiar with graphing equations in general, and essentially graphing a function is the same thing. Remember, we replace y with f of x. So if we replace y with f of x, what you really see is that an equation like y equals 2x plus 1, which is a linear equation, becomes f of x equals 2x plus 1. So if you know how to graph y equals 2x plus 1, you really know how to graph f of x equals 2x plus 1. So a graph of an equation and the graph of a function are generally the same definition-wise. The graph of a function is the collection of ordered pairs x comma f of x, such that x is in the domain of f. Normally it's x comma y, but remember, f of x and y are interchangeable parts, so essentially the same thing. Generally, how do you graph equations? I think most people will be familiar with the XY chart method of graphing an equation. You pick some random x's, it doesn't matter, 1, 2, 3, and figure out what y goes with that. So if I look at this equation here, y equals 2x plus 1. If x equals 1, y equals 3. If x equals 2, y equals 5. If x equals 3, y equals 7. So this would be my points that I use to graph the function. I connect these dots, these are points on the xy plane, and I draw my graph. Well, if I'm going to graph f of x equals 2x plus 1, I'm pretty much doing the same thing, but it's an f of x chart. But generally, this is the same chart. 1, 2, 3 would be some random x's I pick. F of x would be 3, 5, 7, and my xy plane becomes my f of x plane. Instead of a y-axis, you have an f of x axis. So you generally graph functions the same way you graph equations. Now, we'll talk more about that later. Right now, what we need to do is, if I give you a graph, can you tell me whether or not that graph represents a function? Does that graph follow the definitions of functions? So, does every x get matched to exactly one y? Well, there's something we can do called the vertical line test. The vertical line test says if you put a vertical line anywhere on the graph and it touches that graph at exactly 1 point each time, then that graph is the graph of a function. So if I looked at this particular equation and I was to draw the graph, pick some x's or pick some y's, do an xy chart, what happens is that graph ends up looking like this. Here's my x-axis, here's my y-axis. And if I draw this graph, this does not pass the vertical line test. If I put a vertical line on here, I have 2 places where this vertical line hits my equation. So if it hits my equation in 2 points, what happens? Here's an x value. This x value has 2 different y values associated with it. So 1x goes to 2 y's. That's not a function, and that's how the vertical line test can sort of basically show you whether or not this graph passes the definition of a function or not. So this is not the definition of a function. We already looked at this equation anyway and said, well, we can determine that it's not a function by solving for y. But you can also look at the graph of this equation and determine that it's a function or not. So this is not a function. Okay. Let's look at some other ones. Let's look at this one. Y equals negative x squared. Again, I could graph this using a simple xy chart, connect my dots, and get my picture. We will talk more about graphing in the next section, but if I was to draw the graph of this, here's my x-axis, here's my y-axis, the graph would look like this. It would be this parabola shaped pointing downward. So if you look at this U-shaped picture pointing downward, if I was to draw a vertical line anywhere on the graph of this thing, every single time I'd only hit 1 point. So if you look, every vertical line hits the graph at only 1 point. Therefore, this is the graph of a function. This one here, fairly tricky one. We'll talk more about this type of equation later, but if I give you the actual picture of the graph, this is a circle. It's a circle of radius 2, so that means it hits here at 2, 2, negative 2, negative 2. The center is at this 0, 0. Don't worry if you can't come up with that exact graph from this equation. Just if I give you this graph here, can you tell me whether or not this is a function? Is this the graph of a function? Well, vertical line test, you see that I keep failing and failing and failing the vertical line test. I just have to fail the vertical line test once, but over and over again, my vertical lines hit this function at 2 points. So anytime you hit it more than 1 point, it's not a function. So this one's not a function. So circles are not functions. These U-shaped, which we're going to call parabolas, these are functions. The last thing we need to talk about is the applications of functions. There are plenty of applications of functions. We're just going to talk about one specific one, which is the general idea of slope. Slope is generally thought of as the average rate of change. When we look at the average rate of change, we think of it as the change in y over the change in x, which you pretty much know to be slope. And we've labeled slope in previous algebra classes, I'm sure you've had, as m. But generally, this average rate of change is an application sort of functions, and it's an application of really the slope of functions. So when we look at this slope of a function, or this average rate of change of a function, we need to know the change in y over the change in x, or y2 minus y1 over x2 minus x1, which means if I have 2 points on the graph of a function, I use those 2 points, x1, y1, x2, y2, to find the average rate of change. So if I look at this question, find the average rate of change for this function over this interval. Well, this interval, these are x values. Okay? So basically what we're saying is if x equals 1, we need to know the y value. So we need to find f of 1, which would be 1 squared plus 3, or 4. And if x equals 3, we need to find f of 3, which would be 3 squared plus 3, or 12. So if I want to find the average rate of change, or the slope, I should do y2 minus y1 over x2 minus x1. I could also write this as f of x2 minus f of x1 over x2 minus x1. In that case, I'm going to get 12 minus 4 over 3 minus 1. This would be my f of x2, and this would be my x2, and so on. So I have 12 minus 4 is 8, 3 minus 1 is 2, 8 over 2 is 4. So the average rate of change, or the slope of this function over this interval, would be 4. Now that's the average slope. That's not the exact slope, but the average slope, the average rate of change, or the average slope, would be 4. One major building block of calculus is the concept of slope. Now, we found the average slope, but you may want to find the instantaneous slope, or the exact slope, not over an interval, but at a point. That is the whole idea of how calculus is built. Now, we're not going to do calculus, but we're going to give you one of the building blocks towards that, which is the idea of the difference quotient. The difference quotient is very similar to the average rate of change, and it's essentially the mechanism for which the average rate of change becomes the instantaneous rate of change. Now, what we want to do is find what we call the difference quotient. Now, the difference quotient is a specific fraction that is basically built off of a lot of the things we've already talked about. The difference quotient is f of x plus h minus f of x all over h. Okay? Now, we know how to find f of x plus h. We've already done it. We know how to find f of x. That's actually going to be given, and then this h is here. So what I really want to do is essentially plug these things in here and simplify this fraction. But this fraction is the difference quotient. So if I look at this fraction and I want to find the difference quotient for this particular function, what I'm going to do first is find f of x plus h. So that's 3 times x plus h plus 2, which is 3x plus 3h plus 2. Okay? So I have f of x plus h is this, f of x is this, and now I'm going to plug this into my difference quotient. So my difference quotient is f of x plus h minus f of x all over h. So if I plug this in here, I plug this in here, what do I have? I have 3x plus 3h plus 2 minus 3x plus 2 all over h. Now, what's going to happen lots of times is that you're going to cancel a lot of things out. Your goal for most of these, and really right now in our class for all of these, is you want to somehow cancel this h out of the denominator. The reason is, when we look at this, the purpose for this again is for calculus, and this average rate of change is that h is going to be getting closer and closer to 0, which is fine, but when h does actually get to 0, you would have 0 in the denominator, and you can't have that. So if we cancel the h, then that's no longer a problem. Well, in order to do this, we got to simplify. So what we have to do is distribute this negative through. This is key. I see students make a mistake here all the time. F of x is being subtracted. All of f of x is being subtracted. So this negative has to distribute through all of f of x. Here was my f of x. Remember, f of x plus h. I plugged f of x plus h in here. I plugged f of x in here. And this is what I got. So if I distribute, I end up with 3x plus 3h plus 2 minus 3x minus 2 all over h. What happens? Well, this 3x and this minus 3x will cancel. This plus 2 and this minus 2 will cancel. And I end up with 3h over h. Well, guess what? Those h's cancel. So what do I have? I have that my difference quotient equals 3. Again, what does that mean is not really that important right now, but it will have something to do with the instantaneous rate of change in the future. Right now, all you need to do is come up with that answer. Now that answer is 3. It's not always going to be a number like 3. Sometimes it'll be a function, but that's the answer for this particular one. And the key was we got rid of that h. If you see how things are canceling here, we canceled all these values here. That's going to be a fairly common occurrence. Let's do another one. G of x equals x squared plus 2x minus 1. So if I want to find the difference quotient, first thing I'm going to have to do is find g of x plus h. So that's going to be x plus h squared plus 2 times x plus h minus 1. In that case, it's going to be x squared plus 2xh plus h squared. Remember, if we square x plus h, you have to do it all out, plus 2x plus 2h minus 1. I can't simplify that any further, so that right there is my g of x plus h. This is g of x. So what I need to do is to find the difference quotient. I need to find g of x plus h minus g of x all over h. So I'm going to take this and I'm going to put it here. I'm going to take this and I'm going to put it here. And I'm going to get x squared plus 2xh plus h squared plus 2x plus 2h minus 1 minus g of x, which is x squared plus 2x minus 1 all over h. So this negative's got to be distributed in here, and what I end up with is x squared plus 2xh plus h squared plus 2x plus 2h minus 1 minus x squared minus 2x plus 1 all over h. Well, guess what? X squared minus x squared, cancel. 2x minus 2x, cancel. Minus 1 plus 1, cancel. Look at what we have left. 2xh plus h squared plus 2h all over h. My goal, cancel the h out of the denominator. Well, guess what? Every one of these terms has an h in it. I cannot just cancel one h here with, say, one of the h's here. That's not going to work. But what I can do is, since they all have an h in them, factor the h out, have 2x plus h plus 2 all over h, cancel these two h's now, and then what I have is my difference quotient is 2x plus h plus 2. And you see, we don't just get a number in this one. What I get is this function of two variables, or this, algebraic polynomial. So the last two examples were polynomial functions that we found the difference quotient of. And most of those will work out exactly the same way. You're going to find your f of x plus h or g of x plus h. You're going to plug everything into the difference quotient properly, and then a bunch of stuff's going to cancel, and then eventually you can cancel the h's. But functions that aren't polynomials, this whole difference quotient business works out a little differently, but the goal is the same. We want to try and get that h out of the denominator. So we start this problem the same way. The problem is this is not a polynomial. So if I want to find the difference quotient, first thing I'm going to do is find h of x plus h, which means I find the square root of x plus h. Alright, so that was easy. That's just h of x plus h. Well, alright, so what do we want to do? We want to find the difference quotient. The difference quotient should be h of x plus h minus h of x all over h. Now, this is not the best, but this h is not the same as this h. Okay? This is the h that's the name of the function, and this is just the h from the difference quotient. So anyway, what are we going to do? We're going to take this and plug it in here. We're going to take this and plug it in here. And we're going to get square root of x plus h minus the square root of x all over h. Problem. Things aren't going to cancel as nicely as with the polynomial ones. I can't just multiply out, collect like terms, cancel, and then get rid of that h. These square roots are the issue. Well, there's some skills you learned along the way in algebra. One is rationalizing. You rationalize denominators a lot, but you can also rationalize a numerator. And the idea with these is you want to multiply by the conjugate. Now, you're not going to have to do a ton of this. I would tell you most of the examples you're going to see right now in the homework and that you would see, say, on tests or quizzes would be the previous ones, the polynomial ones. But I did want to give you one example that was different from those. So what I'm going to do here is I'm going to multiply this fraction now by the square root of x plus h plus the square root of x. That is the conjugate of this piece right here. Conjugate means it's the same two terms added or subtracted together. Now the problem is I can't just do that, but what I can do is multiply the denominator by the same thing, and therefore I'm multiplying really by a 1. This whole thing right here is really 1. So if I multiply by 1, now I'm not changing it. And what I'm going to do is, okay, if I multiply out the numerators, whenever you multiply conjugates, right, if I have a plus b times a minus b, these are conjugates of one another, same two things added and subtracted. What I invoke is the difference of two squares formula. So that's what I'm going to use here. So in order to do this difference quotient, I'm going to multiply the conjugates in the numerator, which is going to give me the difference of two squares. So I have this x plus h squared minus the square root of x squared. That's the numerator multiplied out. I could do it the longer way, this times this times this, and so on. But you got to understand that when I multiply conjugates, I have the difference of two squares. The denominator is going to be h times the square root of x plus h plus the square root of x. Basically, I'm just multiplying this times this, but I'm not actually multiplying it out. So what happens here? Square a square root, I get x plus h. Minus square another square root, I just get x. All over h times the square root of x plus h plus the square root of x. And now things are going to cancel. This x and this x cancel. I just have an h here, but then that h and that h are going to end up canceling. And what happens? I canceled everything out of the numerator, which means there's a 1 left over. Not a 0, 1. The denominator, what do I have? I have the square root of x plus h plus the square root of x. this right here is my difference quotient. Now it's kind of contradictory to some of the things you learned in algebra, which was you shouldn't have roots in the denominator of a fraction. But we're going to deal with that issue, later, in that, okay, we don't want roots in the denominator, but we needed to have roots in the denominator so that the h by itself is no longer in the denominator. So one trade-off for another. But I wanted to show you one example that was different than the last two, in that this was not a polynomial, and therefore this method of trying to find the difference quotient is far different. Whenever you have these roots, specifically the square root ones, this multiplying by the conjugate situation is going to be something that you're going to need. So some little tricks you've learned along the way in algebra that will help you with the difference quotient. But I'll tell you, most of your difference quotient questions will be for functions that look like this. Find the difference quotient for this function, say 5x squared plus 3. Polynomial function in that case. Do it the same way we did the previous examples. So if it's a polynomial, looks like the last two examples, a square root looks like this. I could give you 20 other functions in the difference quotient work out differently. We're not really going to get into that. If you do end up taking calculus, you will see a lot of that in there.